So just to clarify, with data sufficiency, I didn't put the answer choices here, but they're always the same. You just have that A is that statement 1 by itself is sufficient, while statement 2 is not. Then you have B, which is statement 2 by itself is sufficient. Then you have C, which is 1 and 2 together, but not individually. And then you have D, which is each individually. And then you have E, which is that even together, they're not going to be sufficient. So it's always exactly the same answer choices. So just to clarify, when we say sufficient, we mean that we can get a definitive answer to the question. So basically, there's no doubt as to what the answer is. And with these questions, it's tempting to go straight to the statements to figure out if they're sufficient. But what you actually want to do is you really want to focus on the question itself. First, figure out what kind of question it is. So by that, I just mean if it's a value question where you're trying to find a specific number, or if it's a yes or no question. So in this case, we want to know if this number, k times y, is a multiple of 174, which means that we're just trying to answer with a yes or a no. So we don't actually care about finding the exact value of k times y. We just want to know if it is a multiple or not. So basically, we want to figure out if k times y can be written as 174 multiplied by something. And right away, before, again, you go to the statements, you want to think about what this actually means. So 174, we can reduce that. We can find the prime factors of it. And it's obviously an even number, so it's definitely divisible by 2. Also, if you add together the digits, so if you do 1 plus 7 plus 4, that's going to give you 12. And there's a rule that says that if the sum of the digits is a multiple of 3, then it's going to be divisible by 3. So if you see that it's divisible by something else as well, then overall we can see that it's going to be divisible by 6. We can say that if we divide it by 6, it's not super easy to calculate, but keep in mind that 180 is divisible by 6. And 180 divided by 6 would be 30. This is actually 174, which we can think of as 180 minus 6. So that's going to end up giving you 180 over 6 is 30, 6 over 6 is 1, so that's going to be 29. So that's just kind of a shortcut so that you don't have to do it out by hand. And so this is the same as 6 times 29. And then you can reduce the 6 since it's not prime. We can rewrite that as 3 times 2. And just to clarify, 2 is the only 2 is the only prime number that you have. So this is what we've reduced it to. And if we focus on the prompt now, so basically we've kind of already been doing that, but the prompt also tells us that k is a multiple of 29. So you can think of k as 29 multiplied by something, which could be 1 or any number. And we can see then that we already have the 29 that we need in order for the k times y to be a multiple of 174. So what we also need to have in the prime factorization, either from the k or from the y, because remember we also have the y here, is going to be a 3 and a 2. So that could be a 6 altogether, or maybe it's kind of divided. Maybe the 3 is with the k and the 2 is with the y or something. So the key thing is to kind of figure out exactly what you're looking for right away so that you can use the answer statements more quickly. And when you're looking at the statements, you don't necessarily want to start with the first one that you see. In this case, I would probably actually start with the second one because they're kind of saying it in an overcomplicated way. But k is divisible by 2 without a remainder really just means that k is even. So 2 goes into it evenly. And that's just very simple to work with. So I would actually start with statement 2. So generally, either the one that seems the easiest to work with, or if there's one that seems clearly insufficient, that's usually the best one to start with, just because then you can at least eliminate some answer choices with certainty. So if k is even, then that means that the prime factorization of k definitely has a 2 inside it. So we already know from the prompt that it has a 29. Now we also know that it has a 2. So since we're taking k times y, we now know that the k part has a 29 and a 2 for sure. The y, we don't actually know anything about it at the moment. And remember that in order to be a multiple of 174, which we factorized as 3 times 2 times 29, then we would also need to have a 3. So the problem here is that we don't know if there's a 3 in there or not. And so since we don't know if the 3 is in there, it's not going to be sufficient. We just don't know for sure if this is going to be divisible by 174. So that's going to make it not sufficient. If instead they had said it was divisible by 6 or a multiple of 6, then it would be sufficient because now you would have a 6 in there. So for sure it would work. And then you have statement 1, which says that y is a multiple of 27. So we can write it again as 27 and then times something. Also here, actually, we could have had something else that we didn't know. And 27, we can reduce it to 3 cubed. So now if we're looking at k times y, keep in mind that you don't want to combine the statements yet because we're looking at them individually. We know that the k has, from the beginning, it has a 29 and maybe something else. And then the y has a 3 cubed and maybe something else. So we definitely have a 29 and a 3, but now we don't know if we have the 2. And so for the same kind of reason, this is going to be not sufficient because it could still be a multiple if we also have a 2, but we just don't know for sure. So if we put them together though, so if we consider the statements together, you can see that statement 2 essentially tells you that you have a 2, and statement 1 tells you that you have 3 3s. We only need one of them. The point is that now put together, we will have all the numbers that we need, all the prime factors. So we can say that k times y, k is going to have the 29 and a 2, and maybe something else. And then the y is going to have the 3 cubed, and maybe something else as well. The point is that it does have a 29, a 2, and a 3 for sure. And so then, again, if you put that together, it's just going to go back to 174, which means that our number is going to be divisible by 174. So together they are sufficient, and that's the answer choice C. So that's when neither one is sufficient by itself, but together they are going to be sufficient. So they like to do this kind of thing a lot where they give you a number that's pretty big. So the best thing to do right away is just to factorize it, just to make it easier to work with. And also, as you can see, the statements are actually pretty quick to go through once you know what you're looking for. So if you hadn't done that, then it would just be a bit messy to work with. So one of the main things that I always suggest is to really focus on the prompt, even though it might seem counterintuitive that you want to spend more time on that than on the answer choices. It actually ends up making going through the answer choices a lot quicker. So if anyone has any questions, feel free to ask. If not, we'll go on to the next one, which is also on factoring. So here they tell us that we have a positive integer k with 2 prime factors, and the question is, what is the value? So I would focus on the question right away. So clearly it's a value question. We're just trying to find what k equals. And you always want to make a note of what you're looking for, especially when you have multiple variables. So let's say that we were talking about k and another integer x or something. The point is that we don't care about x, we just need to find the k. So you would just want to focus on what you're actually looking for. And if we now look at the prompt, we know that it's a positive integer. So anytime I see that, I just write plus I, just a way to kind of remind myself that we're dealing with only positive integers, because that might be relevant later. And we know that it has 2 prime factors. So prime numbers are 2, 3, 5, 7, and so on. And they said exactly 2 prime factors. So that means that there's no others. So sorry, I meant to write 3 and 7 here. So that's implying that, for example, 2 and 5, they're not going to be factors, as well as any other prime number. And they tell us that K has a total of 6 positive factors. So notice how first they're talking about prime factors, and then they're talking about total factors. So that's including the primes and also the non-primes. And they include 1 and K. So, so far we know that we have 6 total factors. And the ones that we have so far for sure are 1 and K, which are kind of the 2 extremes. Also 3 and 7. But also because we're talking about all the factors, not just the primes, you also have the factor of 3 times 7. So 21. And then there has to be another one. So if we think about how it's possible to have one more factor, first of all, remember that we have no other prime factors. So no other primes, which means that we definitely don't have any 2s, any 5s, 7s, or anything else. And you also can't have any non-prime multiples of the ones that we already have. So for example, we can't have, let's say, 14, because 14 would be 7 times 2, and that would now add the prime factor 2, which would be contradicting what they tell us. So if you think about how it's possible to only have one more factor in addition to the one for K, you can think about different scenarios, but in the end, keep in mind that even if, like, theoretically you could have another prime number like 2, you wouldn't just have just that one extra. You would also have 7 times 2, so 14, and then you'd also have 3 times 2, so 6. And so that would add a lot more factors. So the only way that you wouldn't add that many factors, so that you would add only one factor, is if the other number that you have is also a 3, or possibly a power of 3. So it can't be 3 actually, because yeah. Did you say something?
Oh no, sorry, my bad. I just unmuted myself. Go on.
Okay.
Sorry.
Don't worry. So it can't actually be a 3, because otherwise we would be counting the 3 twice. And it's implied here that when they talk about 6 positive factors, they imply different factors. So it would have to be a power of 3, or maybe a power of 7. So for example, we could have 3 squared, or maybe 7 squared. Because if you have something like that, it's only going to add one more factor, in the sense that if we have 3 squared, for example, then we'd have 3, 7, and 3 squared, which is 9. So basically the new factors now would be 9, and 1 second. Yeah, just 9, and also we would have, let's see, give me a sec. We would also have K, which is going to be 3 times 7 times 9. So let me just double check one thing. Okay, oh no, sorry, it would have to be a 3, because otherwise, actually, if we had 9, we'd also have to consider 9 times 7, 56, so then we'd have a bunch more. So it would actually have to be another 3, which then put together with this 3 would give you a 9. So just to clarify, basically the new factors here would just be 9. And then if these are all the factors, K would have to equal 3 times 7 times 3. So 63. So it's really important to focus on the fact that they tell you that you have a total of 6 positive factors, and you have to think about how that's possible, that you're only adding one extra factor. by adding a prime factor in there. And so it has to be essentially the same exact number as one that you already have. So it has to be either a 3 or it has to be a 7. So in total, you have a 3 squared and 7 squared. But individually, it has to be just a 3 or a 7. So now that we know what we're looking for, we know that essentially they have to tell us that there's another 3 in there or another 7. So if we look at the statements, they're pretty similar, so we can just start maybe with the first one. They say 3 squared is a factor of k. So that means that you have 3 to the 2. So you have 2 3s essentially in the prime factorization. And so that's the example that we just talked about. So then you know that you have another 3, which is going to mean that your new factors are 9, and then your other factor is k, which is going to end up being 63. So this would be sufficient. So again, we're looking for either a 3 or a 7. Then in statement 2, they tell us that 7 squared is not a factor. So you don't have 2 7s, which means that you only have 1 7. And if you only have 1 7, then you must have another 3. So this leads us to exactly the same answer. In general, the statements cannot contradict each other. So it's not possible for one of them to imply that you have an extra 3 and for the other one to imply that you have an extra 7. They're always going to support each other. So in this case, we can see that each one individually is sufficient to be able to find k. And so therefore, we don't even have to put them together. It's going to be answer choice D, which is just that each statement alone is sufficient. So just to kind of recap, the key thing is, again, to focus on what they tell you right away. So the fact that you have only 6 total factors, so you can just write them all out and then think about what those extra factors can be. And once you know what you're looking for, then it's pretty easy to look at the statements. So you just have to make sure that they tell you directly or indirectly that you have another 3 or another 7. And there's no doubt as to which one it is, so that the statement becomes sufficient. Okay, so in general, you'll see that this concept of prime factorizing comes up pretty often, even if they don't directly tell you that you should be dealing with prime factors. Really, anytime you're dealing with big numbers and you're talking about multiples or divisibility, it's always what you want to do to approach it. And also one more thing that might be useful is I wouldn't immediately look at the statements because first of all, they're usually made to confuse you and to make you waste time. So that's why you tend to want to look at them later after you know what you're actually looking for. But if you have no idea what to do with the prompt, you might want to take a very quick look at them. And if you see that they're talking about 3 squared and 7 squared, that's a hint that you should be considering numbers like that. So that can help you figure out what to look for, but you definitely don't want to immediately go through the statements until you know exactly what you're looking for. So now the next one is a different kind of question. So this is with ratios. Ratios come up pretty often, and the method that we're going to be using here is going to be the unknown multiplier, which is something that's actually really useful in ratio questions. It just makes them much easier to work with. So first of all, we're looking for the number of number of men on the sightseeing tour. So this is a value question. So we're looking for M. And if we focus on the prompt, and so especially for this one, I would definitely make a note of the fact that you're looking for the men, so we don't care about the children or the women. So we don't necessarily need to find those. And in the prompt, we know that we have women to children is 5 to 2. You could use the unknown multiplier right away. So what the unknown multiplier is, it just tells you basically how many groups of 5 women and 2 children you can make. So we can think of the number of women as 5x and the number of children as 2x. So x is the unknown multiplier. So the idea is that, for example, you could have maybe exactly 5 women and 2 children, or you could have 10 women and 4 children, so any multiple of that. So see how this one you could rewrite as 5 times 2 to 2 times 2. So in this case, the unknown multiplier, so the groups of 5 women and 2 children is going to be 2. So then x would be 2. So it's much better to work with unknown multipliers rather than just ratios, because this way you can immediately find the numbers that you're looking for. So this way, if you know that you're looking for, let's pretend we were looking for the children, then we know that we're looking for 2 times x. So once we find x, we just have to multiply by 2, and then that's going to be your answer. Or if they wanted the difference between the number of women and children, then you'd want to look for 5x minus 2x, that's women minus children, so 3x. And so it's much better to work with the actual number of women and children rather than the ratio of them. So far we don't know anything about the men, so the prompt is not very useful. If we look at the statements, I would probably start with the simpler one first. So doesn't matter too much, but the second one is a little bit simpler just because it only talks about the women. So if we start with that one, we know that women is less than 30. So if we want to use what we just wrote above, we said that women can be represented as 5 times x. So 5 times x is less than 30. This would allow us to find the unknown multiplier. But actually right away we can see that because we have no information about the men, and the men are the ones that we're looking for, it's actually not going to be useful. So since it just takes a second, we might as well do this out. But it's definitely insufficient because we know nothing about the men. And here I meant to write x. So this represents the number of groups of 5 women that we have. And basically we're saying then that it has to be 1, 2, 3, 4, or 5. Because keep in mind that obviously if we're talking about people, they have to be whole numbers. So this is definitely not sufficient. Then statement 1 says that we have the ratio of children to men. So we can say that men to children, or well, children to men, is 5 to 11. We might as well immediately put that together with the information that we have from the prompt. Again, you don't want to look at the other statement yet because we're not combining them immediately. Although with this kind of question, if we're talking about a number of men and we're given 2 ratios, there's no way that 2 ratios without more information are going to give you a specific number. It's just not possible. So we already know it's not going to be sufficient. And so then we're going to have to put the 2 statements together. So if you already knew that statement 2 worked, then you don't have to bother going any further with statement 1 because it's clearly insufficient since 2 ratios just won't give you an actual number of people. But because we do have to put them together afterwards, we might as well combine this with the prompt. So we had that the women to the children were 5 to 2, children to men were 5 to 11. So we can just turn them all into, like, put the ratios together and turn it into just one big ratio. So if women to children was 5 to 2, and then the other one was 5 to 11, the best thing is to get a least common multiple between the ones that are in common. So in this case, the children. And then just put everything together. So the least common multiple of 2 and 5 is just going to be 10. So I would have to multiply this one by 5, and then this one by 2. So that's going to give you 25 to 10, and then 10 to 22. Or wait, did I mess something up? Yeah, it should be fine. And then we can put them together. So the new ratio in total becomes 25 to 10 to 22. And again, when you have a ratio, you can introduce an unknown multiplier. You do want to use a different one because before we were talking only about women and children, so we had different numbers here. We were talking about different groups, basically. But in the sense that here we're talking about groups of 5 women, and now we're talking about groups of 25 women. So the point is that you want to use a different letter just so that you don't get confused. So we could use Y or something. And either way, though, as we said before, it's not going to be sufficient because we don't know what the number of men is. Only thing that we can say is that the men, which are the last ones, they're going to be a multiple of 22 because Y has to be at least 1. And again, it has to be a positive integer since we're talking about numbers of people. And make sure that you did find a least common multiple and you don't find a bigger multiple because otherwise that could give you, that could mess up the results later. So you just want to realize that the absolute minimum value of Y here is 1. While if you had accidentally thought that maybe the least common multiple was 20 or something, then we would end up with like 50Y, 20Y, and 44Y. And the problem with that is that now we'd have to consider actually Y as fractions as well, to see how now Y could be a half because they're all divisible by 2. And because you want to make it easy and just have to consider positive integers, you want to make sure that this is reduced as much as possible. So make sure that you do take a least common multiple and you don't accidentally have something that you can reduce further. But in this case, these ones are not divisible by any number, like altogether. So we know that the men is equal to 22Y. So if we were able to find Y, then we could say how many men we have. So if we now put the statements together, statement 2 told us that we had women that were, the number of women was less than 30. So the number of women is now this one, if we use the other statement. And if 25Y is less than 30, remember that the unknown multiplier has to be 1, 2, 3, 4, 5, and so on. So actually the only possible unknown multiplier that would work here, since again, it's not like we can have decimals or fractions, would be 1, which means that we would have exactly 25 women. So we don't care too much about the women, but we care about the fact that Y is 1. Because now since Y is 1, you can just plug it in and get the men, which are going to be 22 times 1. So just 22. So they could have also done a different kind of question where maybe they told you the total number of people. So the total number of people here would be 25Y plus 10Y plus 22Y. So that's going to be 35, 57Y. So in this case, we don't care about that. But let's suppose that they told you the total number of people is less than 100. Even though that might seem very vague, we actually know that this has to be less than 100. And again, the only unknown multiplier that could work is going to be 1, because if it's 2, then that's already going to contradict the fact that it's supposed to be less than 100. So the point is that by using the unknown multiplier and finding a way to represent the actual numbers of people rather than just the ratios, you can easily tell if you only have one option for the unknown multiplier or if there are several. So if instead the question had been, or the statement had been, the total is less than 120, then that's different because now you can see that Y can be either 1 or it can be 2. And now we don't actually know for sure. So the point is, though, that it's always good to use the unknown multiplier just to be able to kind of use the information more quickly. And also they could have given you the information also in a different way again. So they could have said like the difference between men and women. So men minus women is, or actually women minus men, because we have more women than men. Women minus men is, let's say, less than something, so less than 5. And again, if you use the same kind of information, we know that the women are 25Y, the men are 22Y, So basically we'd be saying that 3y is less than 5. And it's the same kind of concept. So y has to be at least 1 or any other positive integer, but the only one that could work is 1 again. So you keep on getting the same result, just in a different way. So this concept comes up pretty often. And again, it's always best to just use the unknown multiplier every time so that it's easier to work with whatever information they give you. Okay, so feel free to stop me if I'm going too fast or if anything isn't clear with this. And now we have two questions, which are going to be pretty common types of questions when we're talking about two possibilities, or actually four possibilities. Like in this case, you're talking about buying product P or Q, and you can buy one but not the other, or both, or neither. So everything is possible. So even though you could try to do this with the Venn diagram, you really only want to use Venn diagrams when you have to, which is when you have three options. And so then you'd have the three circles, just because you obviously can't have like a three-dimensional table to represent all of this information. But if it's only two options, which it really always is, then it's much better to use a table instead. So the table that I'm referring to is the one where you list all of the mutually exclusive possibilities. So for example, we know that we can either buy P or not buy P. So I just write it as P and no P. And then you can buy Q or not buy Q. So then you have Q and no Q. And we're looking for the fraction that bought neither product P nor product Q. So that would be this one here that we're looking for. So the prompt really doesn't tell us anything. And the statements are pretty similar. Notice how both statements are fractions. So everything is a ratio here. And so what's nice about that is that even though they don't give you actual numbers, that means that you can pick your own numbers just so that you don't have to deal with complicated fractions. Ideally here, because we see that we're talking about 1/3 of the total people and a half of the total people, is you want to find a number that's divisible by both 3 and 2. So you could pick something like 300, for example, or even like 6 or something. Doesn't really matter. So I was just thinking 300 because usually we use big numbers here, like 100, but it doesn't really matter in the end what you pick. So we can just start with statement 1. And just to clarify, this method of picking a smart number, we can only do it because we're not given any numbers at all. If one of the statements had said you have 50 people here, then obviously you can't pick any numbers you want because that's going to mess up the results. But if they don't give you any numbers, then it's okay to do that. So if we use 300 as the total of everything, we know that 1/3 of the total said they bought product P but not Q, so that's 100 people. And that would be P not Q, so that's going to be over here. That really doesn't tell us anything else. So we know that this sum here is at least 100, and this sum is at least 100, but it's not very useful. So this one is definitely not sufficient because what we're looking for is the one below. So, I mean, we're looking for this one. Make sure that you do another table, even though it's a little bit annoying to draw all of these tables. You don't want to put the information together right away because otherwise you'd already be combining the statements. So we still know that we have a total of 300. And now we know that a half of the people surveyed bought product Q. So 150 people out of the 300 bought Q. So that's going to be this one. And if you know that this is 150, then also this is 150. Which again is not actually going to be sufficient because it doesn't tell us the value that we're looking for. So again, it doesn't tell us this one. But notice how now if you combine the two statements, now we know that the one over here is 100, and the total here is 150. And so this one must be 50. And that's what we were looking for. So together they are going to be sufficient. So that's going to be answer choice C. So make sure that you fill in everything right away, so you realize that if you have this value, then because you know the total is 300, you can figure this out as well. Okay, so now we have another one that's similar to this one, but a bit more difficult. So here we have 100 students studying Japanese, and 4% who study French also study Japanese. So it's a similar kind of question. You can kind of recognize these pretty easily. You're always talking about two groups and how people can be either in both groups or just one group at a time. So first of all, we're dealing with, we want to figure out if we have more French than Japanese. So notice how you're not looking for an actual number. We're just trying to answer if one is greater than the other. So we want to know, is F bigger than Japanese? Which you could also think of as, is French over Japanese bigger than 1? Doesn't matter how you look at it. And we know that the total Japanese is at least 100. And 4% who study French also study Japanese, so that's the conditional probability. We could write that as probability of Japanese given French is equal to 4%. Now with this question, I definitely wouldn't pick smart numbers. Like I wouldn't pick a number to use as a total or anything, because we do know that the Japanese, we don't know exactly how many there are, but they're at least 100. So we don't want to come up with random numbers ourselves. And also because in statement 1, they talk about 16 students. So that's giving you a specific number, like an absolute number. So you definitely don't want to pick your own numbers here. So keep in mind, again, we're looking for if one is bigger than the other, we don't actually have to find the individual values. So if we start with the statements, statement 1 might be a tiny bit easier just because it's giving you an actual number rather than a percentage. So just like before, we have French and not French, and then Japanese and not Japanese. Make sure you fill in the info from the prompt. So we know that there were at least 100 for Japanese. So the total here is greater or equal to 100. And 4% of French also study Japanese. So that's going to be this portion. We can write it as 0.04 multiplied by F. And F is just going to be this one. So we want to know, is the total of French bigger than the total of Japanese? So basically we want to know, is F bigger than J, which we know is bigger or equal to 100. But really this doesn't actually tell us much because we don't know the relation of this one to this one. So for example, you could have maybe 100 French people, and that would make this one value 4. Or we could have 50 French people, and that would make the number lower. So that really doesn't tell us anything, anything useful. And, oh wait, sorry, one second, I forgot one thing. Yeah, actually they told us, I was forgetting about this part, that they tell us it's 16 students. So far, actually, we were just looking at the prompt. We still know that that number of 0.04F is equal to 16. So this was correct, it's just that I forgot to consider this portion. So by giving us this condition, we could find f, so we can find a number of French people, so that could definitely be useful. You could just rewrite this as a fraction, as 4/100. And so then f is going to equal 16 times 100/4, and that's going to simplify to 400. So now we know that we have exactly 400 people studying French. So we'd have to compare that to the number of people studying Japanese. Now with the Japanese, they did tell us that it's bigger or equal to 100, but that's really not very specific because maybe the Japanese are exactly 100, in which case French is more than Japanese. Or maybe you actually have that Japanese is maybe 500. We really have no information, no precise information about what that is. If instead we had found something like French is 50, for example. So if we pretend that was actually 50, this number here, then we could say for sure that the French is definitely less than the Japanese. But in this case, we just don't know with 100% certainty. So this one is not going to be sufficient. Then statement 2 is saying that 10% of students who study Japanese also study French. So 10% of J is going to equal the intersection of F and J. So if we call this J, this is going to be 0.1 J. And now that's all we know with this one. So we really can't do much with this either. We could just say though that if 0.1 J, oh no, we don't know what that's equal to actually. Well, we do know that if this is 0.1 J, and then this one was 0.04 F, then we can say that 0.1 J is equal to 0.04 F. And actually now we have a relationship between J and F. So you don't actually have to go any further. You could already get a ratio of J to F. So basically you could take the F to the other side. And then you could divide by 0.1. So that's like multiplying by 10. And we would get 0.4. So actually that's already going to give us enough information because we can say, or you can rewrite it as well, as J equals 0.4 F. The point is that we have less Japanese than French. So this is also why you want to kind of organize all of the data, because in this case, you have to be careful to consider this portion, the 4% of students who study French also study Japanese. That was applicable to both. And then statement 1 in this case wasn't necessary. So knowing that that number was 16 wasn't actually necessary to be able to say that the Japanese is less than the French. And so in this case, the answer would be yes, so it would be sufficient. Just to clarify, even if you had found that French is actually more than Japanese, if you had found that French is less than the Japanese, that would still be sufficient. It would give you a no answer instead, but that's still sufficient. You still have a definitive answer to the question. Okay. So notice how here you it's also useful to figure out if it's a yes or no question, because you can figure out right away what kind of result. Yeah. Did you say something? Okay. So you can already figure out what kind of result you are looking for. So in this case, we just want to know if one of the two is bigger than the other. We don't actually care about the actual numbers. So make sure that you don't waste time trying to find the actual numbers. Okay, so we should have one more question.
Oh, yeah.
Hi, do you have a question? Okay. So this last one isn't too difficult. It's a kind of a typical question where you have powers or exponents. And first of all, they're asking you, is this equal to 8 to the 10? So it's going to be a yes or no question. And we can simplify that right away because we can see that 4 and 8 are both powers of 2. So you can think of 4 as 2 to the 2. So it's 2 to the 2 to the x plus y. And this one is 2 cubed to the power of 10. So then if you simplify, here you have 2 to the 2 x plus y. You can just multiply them. And here you have 2 to the 30. Notice I'm always putting a question mark just to make sure that you don't think that this is something that they're telling you for certain. We don't actually know if this is true or not. That's what we're trying to figure out. So now that the bases are the same, we can just focus on the exponents. So we're trying to see if 2 times x plus y equals 30, which is like saying it's x plus y equal to 15. So the point is that we care about the sum of x plus y. So we don't care about the individual values necessarily. So finding x and finding y isn't necessary. So usually I would say to focus on the prompt, but the prompt doesn't actually tell us anything here. And then we can just look at the statements. So here you should be able to see pretty quickly that neither of the statements is actually going to be very useful by itself. The first one is kind of a typical one where you're trying to find the sum of two variables, and they gave you the exact opposite. They gave you the subtraction. So those don't have a direct relationship. So in general, when you're looking for x plus y and they give you x minus y, it's just not going to be sufficient to answer the question. So it's telling you the difference versus the sum. So this one is definitely not going to be sufficient. Then if instead we look at statement 2, that one is telling you y over x is equal to 1/4. That one also is going to give us a relationship between y and x, but that's not going to be sufficient either. It's just we're going to be able to rewrite x plus y as just using one variable, but it's really not going to change anything. So if you want, you can maybe solve for y, but it's really not useful at all. So all you can do with this is kind of insert it back into the question. So instead of saying x plus y equal to 15, now we're trying to figure out is x plus 4x equal to 15. So it's 5x equal to 15, which means it's x equal to 3. But it doesn't change the fact that we just don't know anything about the x and the y. So we definitely have to put them together. In general, when you see two equations like this, where you have they're two independent equations, meaning that they're not related to each other, they're not multiples of each other, then in general, you will be able to solve for both variables. So you could set up a system of equations. It's not really necessary because you can kind of see right away that, again, if you have two independent equations, you will be able to solve for both variables. And we don't really have to do the whole thing just because it's a data sufficiency question. So we're not trying to necessarily find the exact answer. We just want to make sure that we have enough information to answer it. So at the real exam, I wouldn't waste time finding the actual solution to x and y because it's just not required. But just to kind of see it, we could say that x minus y equals 9. And then again, we had y equals 1/4 x. Or I think I guess I messed it up before. That was x over 4. So yeah, this was actually a bit off. So this was x equals 4y actually. So then it would be as y equal to 3. But anyway, then you could simply put one instead of the other and just do a normal system of equations. So then you get negative 3x equals 9, which means that x equals negative 3. And then once you know x, you know that y is going to be 4 times that, so negative 12. And so if you put it back into the question, we'd have negative 3 plus negative 12, so that's negative 15, not positive 15. So the answer is going to be no. But regardless, it's still sufficient. So it's still going to be answer choice C. So this is kind of a lower level type of question where you should be able to immediately say really that even without doing anything out, individually they won't be sufficient, but together they will be.